unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
Hey everyone, and welcome. I'm Fakhruddin Saeed, and I'm so excited you're here for the first week of our module on Deep Learning and Generative AI. Think of this as our starting line. Over the next few minutes, we're going to take a look at a map, a kind of practitioner's guide that's going to walk us all the way from the absolute basics of AI right up to the stuff that's making headlines today. And here it is. This is our map for the whole journey. We're going to start, right at the beginning with the foundations, the really core ideas. Then we'll work our way up through some of the heavy hitters, the concepts and architectures that really define modern AI. I'm talking about things like CNNs and RNNs. And from there, we'll push right to the frontier, to the cutting edge. See that path? That's what we're about to explore together. It's going to be an adventure. Okay, but wait. Before we take our first step, we've got to ask a really basic question, right? Why are we even doing this? Why learn from data at all? Why can't we just stick to the old way? Programming computers with a bunch of rules like we've always done.
Well, the thing is, for some stuff, rules are great. They work perfectly. Think about an e-commerce site, right? If a user clicks Add to Cart, the program checks if the item is in stock. Simple. If this, then that. But what about these other problems? Could you really sit down and write a bunch of if-then rules to predict the weather just by looking at satellite images, or to identify every single person in a huge crowd? No way. It becomes impossible fast.
And that's the whole point. For so many of the really interesting, really important problems out there, we just can't write down all the rules. It's not that we're not smart enough. It's that the patterns are way too complex, or they're always changing. So instead of trying to be the all-knowing teacher writing the rules on the board, we become more of a coach. We give the model the data, and we let it figure out the patterns for itself. That's the big idea behind machine learning.
Okay, so if the machine is learning, how does it actually do that? What's the magic sauce? What's the mechanism that makes this whole thing go? Let's pop the hood and take a look at the engine of learning.
It's actually this really elegant loop, and it's super powerful. Here's how it works. First, you feed some data into your model. The model takes a guess, it makes a prediction. Think of it like a student trying to answer a question on a test. Step 2, we use something called a loss function to compare the model's guess to the actual correct answer. This is like the teacher grading the test, figuring out how wrong the student was. Step 3, an optimization algorithm looks at that error score and says, okay, how can we do better? It figures out exactly how to tweak the model's internal knobs, we call them parameters, to get a little closer to the right answer next time. And finally, we just update those parameters, and the loop starts all over again. Predict, compare, adjust. Predict, compare, adjust. Thousands, even millions of times.
Now, out of all those pieces, you could argue that the loss function is the real MVP here. Seriously. Think of it like a compass for the whole learning process. It's the one thing that's constantly telling the model, you're a little off, go this way. It gives the entire system a direction by putting a number on exactly how wrong the model is. So the entire goal of this whole training game, just find the settings that make that number, that loss, as tiny as possible. So what's this engine built out of? Well, it's all powered by math. But don't let that scare you. Think of them as our power tools. We use linear algebra as the language to talk about data. It lets us wrangle images, text, and sound into neat packages called vectors and matrices. We use calculus, specifically derivatives, as our tool for change. It's what tells us which way to turn those knobs to make the loss go down. And we use probability to handle the fact that, the real world is messy and uncertain.
All right, so we've got our engine. We understand how it works. Now, let's actually build something with it. And we're going to start with the simplest thing you can possibly imagine, just a straight line.
This is called linear regression. So check out this graph. We've got 2 data points. A contractor works 2 hours, the invoice is $250. They work 3 hours, it's $350. The goal is to figure out their pricing. So our model is just the equation of a line. And by running that learning loop we just talked about, minimizing the error, which is just the distance from our line to those dots, the model figures it out. It finds the perfect line, and in doing so, it discovers the pricing structure, $100 an hour plus a $50 flat fee. Super simple, but pretty powerful, right?
But here's the catch. The world is almost never this neat and tidy. Real-world data is messy, it's curved. So what happens when your data looks something like this? How on earth is a model that can only draw straight lines supposed to separate the blue dots from the orange ones? It just can't. It's a dead end.
And this is where we make the jump from machine learning to deep learning. The big breakthrough is this little thing called an activation function. If you just stack a bunch of straight line layers, you just get another straight line. It's useless. But if you stick one of these activation functions in between each layer, it adds a kink, a nonlinearity. And when you stack a bunch of these layers with kinks, suddenly your network can learn to bend and twist and fold the data space in really complex ways. It's not drawing lines anymore. It's like it's doing geometric origami to pull the different classes of data apart.
Okay, so now that our models can handle these complex, curvy patterns, we can start building specialized tools, different architectures designed for various specific jobs, like giving our models the power of sight or the ability to understand language.
So, for images, we have things called convolutional neural networks, or CNNs for short. The trick they use is really clever. They have these little filters that scan across the image looking for local patterns. They might learn to spot simple edges first, then corners, then they combine those to find eyes and noses, and finally they put it all together and go, aha, that's a cat. For stuff that happens in order, like a sentence or stock prices, we use recurrent neural networks, or RNNs, and their key feature is that little loop you see. It's like a short-term memory that passes information from one step in the sequence to the next.
But even those RNNs had a problem. Their memory. It was pretty short. They'd forget things from the beginning of a long sentence. To fix that, we didn't just need an improvement, we needed a total revolution.
See, the big issue with those older models is that they had to read a sentence one word at a time, in order. That makes it really hard to connect ideas that are far apart. Look at this sentence. The animal didn't cross the street because it was too tired. To understand what it is, the model has to remember animal from way back at the start. That's tough for an RNN. And this is where the transformer changes the game. Its big invention is a mechanism called self-attention. Instead of reading one word at a time, it looks at all the words at once. It literally calculates how important every word is to every other word, creating these direct shortcuts between related ideas, no matter how far apart they are. It's a total game changer.
And here's the best part. You and I, we don't have to build these ginormous transformer models from scratch. That's not how it's done anymore. The modern way is this two-step dance. First, some big company with tons of computers pre-trains a massive model on like half the internet. This model learns a deep, general understanding of language or images. Then, we can take that super smart, pre-trained model and just fine-tune it on our own much smaller set of data for our specific problem. This whole idea has completely democratized AI. It puts incredible power in the hands of way more people.
So, wow, we've come a long way, right? From simple lines all the way to these revolutionary transformers. So what does this look like when the rubber meets the road? How do we put all these pieces together in a real project?
Well, here's a great example. This is a pretty standard workflow, the kind of thing you do in a Kaggle competition to, say, predict house prices. First things first, you've got to wrangle your data. That's data processing. You're cleaning it up, dealing with missing values, getting all those 79 different features about each house into a nice standard format. Then you pick your model, maybe a solid multi-layer perceptron. You choose your loss function, the thing that tells you how wrong you are. You add in some regularization to make sure your model doesn't just cheat and memorize the training data. And finally, you do hyperparameter tuning, which is basically just fiddling with all the settings to squeeze out the best possible performance. See? It's a whole process, not just about picking one cool algorithm.
But here's a really important lesson. Getting a great score in a competition, that's not the end of the story. Because the second you try to deploy a model in the real world, you realize that building these things isn't just a technical problem, it's a socio-technical one. The world is a messy place, and our models have to be ready for that.
And there are a couple of classic traps that every single practitioner needs to be on the lookout for. The first one is called distribution shift. Let's say you train a medical AI on data from a bunch of healthy college students. It works great, but then you deploy it in a real hospital with patients who are older and much sicker. The data is totally different, and your model is going to fall on its face. The second trap is biased data. You've heard the saying, garbage in, garbage out, right? It's never been more true. If your historical data has biases in it, and let's be honest, it almost always does, your model will learn those biases perfectly and then start making decisions that are not just wrong, but potentially harmful.
Worse still, these things can create these wild feedback loops. Imagine a model that predicts where crime will happen. It sends more police to a certain neighborhood. Naturally, more police make more arrests, which creates more crime data for that area. The model sees this new data and says, "See, I was right," and sends even more police there. It becomes a runaway cycle. As practitioners, our job isn't just to build a model, it's to understand the entire system our model lives inside.
And with that, our whirlwind tour comes to an end. We've literally gone from drawing straight lines all the way to the revolutionary power of the transformer. You've seen the map, you've got the core concepts under your belt. This was just the guided tour. Now your own journey as a practitioner is just getting started.
So what's next? Where do you go from here? Look, the absolute best way to make this stuff stick is to get your hands dirty. So I really encourage you, dive into the book D2L.ai to really nail down the theory. Then fire up the code notebooks and start playing around. Break things, experiment, and most importantly, join the community. Ask questions, share what you learn. That's how we all get better. Thanks so much for joining me on this first leg of the journey. I can't wait to see you in the next part of our module.